Welcome back, everybody. So we were learning about limits, and that idea of limits is it's going to get closer and closer and closer to something, but it's never actually going to reach it. Remember, for limits, we don't really care about what's happening at that moment. We care about what's happening near that moment, right? That's the idea of a limit. We don't necessarily care about what's going on at that instantaneous place. It's what's happening near that place. And then we can kind of estimate what's going to happen right there, right then and there. All right? So that's our idea of a limit. Let's get to, you know what I did want to show you that I did not get a chance to? If I had this here, okay, this was this problem that we'd done on Friday, that weird t squared plus 9 square root minus 3 over t squared. If you were to go to graph this, and I wanted to find the limit as x approaches 0, look at what's happening. It's going here and here. And it looks to be, we said, okay, it's going to be about 0.16 repeating, or 1/6, if you will, right? We said it's probably going to be about 1/6 or 0.16 repeating. If you look at it on this graph, it's like, oh yeah, that makes sense. And it looks to almost be defined at 0.16 repeating, right? Because it looks like it is going through that y-axis. However, if I zoom in, and I zoom in, and I zoom in, look at what happens. Like, look at this window. This is from -10 to this -10 to the -7th to +10 to the -7th. So we're looking at a really, really, really thin slice on the y-axis. Does it actually cross that y-axis? No. Because if I tried to plug in 0 into this equation, it does not exist. Okay? So that's where we can say, well, it's going to lead to 0.16, but was it actually defined at the y-intercept? No. And we're going to see that here as well. I guess I should ask you. Well, okay. I'm letting the cat out of the bag. We're going to look at this one now. Investigate the limit as x approaches 0 of sine of pi over x. Now, I've already run some calculations for you here. I was going to make you do this, but I guess we don't need to. That's just kind of, whatever. We're taking the limit as x approaches 0 of sine of pi over x. The limit as x approaches 0 of sine of pi over x. Now, I've ran sine of pi. Right, so if I put, sine of f of 1, which is sine of pi, right? Pi over 1 or just pi. Well, the y value at 180 degrees is 0. What if I did 1/2? Well, if I'm dividing by a fraction, that's taking the reciprocal of 2, right? So sine of 2 pi. Well, what's the y value at 360? 0. What if I did it at 3 pi? Still 0. What if I did it at 4 pi? Still 0. What if I did it at 0.1, at 10 pi? If I plug in 0.1, that's 10 pi. Still 0. What if I did it at 100.01, so 100 pi? Still 0, right? Because any constant times pi is going to give you a sine value that's 0. What do you think the limit is then? This might almost lead you into saying that the limit as x approaches 0 of sine of pi over, because look, what am I doing with my x values? I'm making them smaller and smaller and smaller and smaller. So this might lead you into saying, well, that must mean that the limit as x approaches 0 of sine of pi over x must be 0, right? Be careful with that. We picked these values, right? What if I had picked an intermediate value? Think about the rotation along the unit circle. We conveniently chose here and here every single time, right? But aren't there different rotations? Like, what if I chose pi over 2 or 3 pi over 2 or whatever it may be? Well, then I might be able to say, well, look, the limit's going to come out to be 1 or -1. But then I would say, well, what if I chose pi over 4 or whatever? Any intermediate in there. Is it ever going to converge to one thing? No. Okay. Take a look at the graph of this. That's what the graph of this actually looks like. The closer and closer I get to 0, I'm not converging to one number. It's actually making the sine wave faster and faster as I approach 0. Okay. This is an idea of the limit not existing. Okay. When it waves like that, we can say that the limit does not exist because it does not converge to one thing. It does not converge to a single value. The limit, or sorry, if I keep making x values closer and closer to 0, it's just going to keep waving all over the place. It's not going to converge to one number. It's going to stay between -1 and 1, and it's going to keep going through 0, but it's never going to converge to one thing. So we would say that the limit does not exist. It does not converge to one thing, so the limit therefore does not exist. Take a look here. Another lie your calculator might tell you. I'm not going to make you plug these things in, but that's what the book did, showing this table. What would you assume the limit goes to? Based on this table, what would you assume that the limit would go to? You would assume that the limit would go to 0, right? And that would look like a logical assumption. Okay? Look, I'm plugging in 1, 0.5, 0.1, 0.05, and 0.01. And I said to you the other day, well, just plug in values until you believe you think you know what it's going to. You're like, I can say that, yeah, pretty definitively it's gonna go to this. I mean, I would be tempted to say after going from 0.05 to 0.01, yeah, it's gonna go to 0, right? Watch what happens if I get smaller. Let me hide this guy. Okay, do you want to refine your answer now? Instead of going to 0, what does it actually go to? 0.0001. Okay? And it's no coincidence that this is tenths, hundredth, thousandth. That's the 10,000th place, right? Look at the equation. Look at the denominator. It's actually converging to 1/10,000th. Okay? We'll look at this later on and figure out why algebraically it goes to 1/10,000. Okay, but for right now, you just have to be very careful. Okay? You have to be very careful about what values you plug in because right now we're in this mode of just saying we think it's going to go here. Like that first problem was like, guess what it's going to be? What do you think it's going to be? Be careful with that. Okay. Examples 4 and 5 illustrate some of the pitfalls in guessing the value of the limit. It is easy to guess the wrong value if we use inappropriate values of x, but it is difficult to know when to stop calculating values. And as in the discussion of after example 2 shows, sometimes calculators and computers will give you the wrong value. Okay. In the next section, section 2.3, we'll develop a foolproof method to calculating limits. Kind of a little foreshadowing there. All right. Not every day that you get to learn a new function. Not every day that you get to learn a new function. This is a brand new function. It's called that. Have you guys ever seen this? Sometimes it's used in like circuits. This is called the Heaviside function. Heaviside function. It's not because something is heavy. That's the guy's name. I actually think his bio is down below. No, maybe not. It's in the book, I guess. Oh, yeah, there it is. This function is named after the electrical engineer Oliver Heaviside. Okay, so this is the Heaviside function. And that's what the graph looks like. Basically, it just says, he used this in electrical engineering to say, okay, I've flipped the switch on. How can we mathematically show that we flipped that switch on? Well, at time 0, it was off, right? And as soon as I do time 0, I click it on. So instantaneously at 0, I've clicked it on. Okay? That's showing like a light switch clicked on. I've completed the circuit. Okay, at time 0, it's clicked on now. Okay, now, let's investigate the limit here. Okay, let's investigate the limit. If I chose values smaller than 0, okay, what if I chose -1? What would be the value of the function? 0. What about -0.5? 0. What about -0.01? 0. And I could continue that. So you would say that the limit as x approaches 0 from the left side is 0. What about approaching it from the right side? What if I chose to run h of 0.5? Well, that's 1, right? Any positive numbers can be 1. What about t as 0.1? 1. What about 0.01? 1. So you would say that as I decrease values, as x gets closer and closer to 0 from the right side of 0, as I keep making x smaller and smaller from the right side, then the limit would go to 1. So we have this idea of the limit being something from one side and another thing from the other side. I would call this the left side limit is going to go to 0, but the right side limit is going to 1. Okay. And yeah, we can make that distinction, left side versus right side limit. As t approaches 0 from the left, h of t approaches 0. As t approaches 0 from the right, h of t approaches 1. So there is no single number that h of t as t approaches 0. So we say that the limit as t approaches 0 of this function does not exist. Right? That's a very important concept that we have to master. Figuring out when the limit does not exist. The limit does not exist in cases where, we had that sine wave, where it wasn't converging to one single thing. It was still defined in all of those places, but it wasn't converging to something. So therefore, the limit did not exist. Well, what if the limits don't match up? There, the limit does not exist either. Okay? So it's not going to converge to one single number, or the other option is it's not converging to the same number. It's converging to something on one side and something else on the other side. So we say that the limit as t approaches 0 of h of t does not exist. Okay. So we have what are called left side and right side limits. We notice in example 6 that approaches something different from the left. Now look at the notation that we're using here. The limit as t approaches 0 negative, as kind of like almost like an exponent. It's not really an exponent. But they're just saying the limit as t approaches 0 from the left. The notation t going to 0 as negative indicates that we consider only values less than that value from the left side. And the limit as t approaches 0 from the right side, t positive. That's saying as t approaches 0 from the right side. Okay, we noticed that those are different values. That's why we said that the limit did not exist. But that's the notation there. And these are called one-sided limits. One-sided limits. When you make the distinction between left side versus right side limit, it's a one-sided limit. Now, the nice thing is the one-sided limits are going to have all the same rules and laws as the full limits do. But it's an important distinction within the notation. We write the limit as x approaches a from the left, and that's how we would read that, the limit as x approaches a from the left. You don't read that as x approaches a negative. Okay, you say as x approaches a from the left, the limit of the function is blank, whatever. Okay. So that would be considered a left side limit with the negative, and then the right side limit would just be the positive. Okay, and the same definition. We're going to get closer and closer and closer to that value until we are arbitrarily close. So we're close enough that the error is negligible, and we can say, well, then those values must be matching. Okay. So we have left side limit, we have right side limit. Yeah, and then this is a very important thing too. I would write this down, that box. Because that is going to be something that we will use to determine if limits exist or not. I've already kind of talked about it, but this is writing it out in limit notation. The limit as x approaches a of f of x is equal to L if and only if you guys have Mrs. Wolf for honors geometry? Did she ever use that? Yeah? Okay. I didn't know if that was just like my teachers only ever did that. Look at the pen Mrs. Naples is using. She's writing it with a giant flower. But that is a notation for if and only if. The limit as x approaches a of f of x is equal to L if and only if the limit as x approaches a from the left side is equal to L and the limit as x approaches a from the right side is equal to L. So that's a statement that works both forward and backward because it's an if and only if. Okay? You can say that if the limit exists and it's equal to L, then you know right side and left side limits are L. Backwards, you can say if the left side limit is L and the right side limit is L, then the full limit is L. So you can kind of prove limits are what they are by using this statement. All right, let's take a look here. The graph of a function g is shown. Use it to state the values, if they exist, of the following. Okay, take a look at A here. I want to find the limit as x approaches 2 from the left. Right? That's what the notation is saying. The limit as x approaches 2 from the left. Now, from the left side, look at 2. Okay, here's my x value of 2. What's it look like it's going to? What's the y value that it's going to at 2? 2 comma 3. Okay, that is correct. Please don't make the mistake of saying, well, it's an open circle, so it's not actually at 3. I don't care what's happening at 2. I care what's happening leading up to 2, right? I don't care that this function is undefined at 2. I care that the function is saying, okay, at 2, from the left side, it's getting closer and closer and closer to 3. Like 1 comma 2.8, 1.5 comma 1.9, and so on. It's getting closer and closer to 2. All right, well, what about, please, there we go. What about 2 from the right? 1. As I keep getting closer and closer to 2 from the right side, the y value it keeps getting closer and closer to is 1. So what can I say about the full limit? It doesn't exist. Okay? And you can just write DNE for does not exist. That's what I use. You can write it out. There's no symbol. Don't do the no solution symbol. The limit does not exist. Okay, let's take a look at the next set, because it looks like I have the exact same thing, but now going to 5. 5 from the left. What is the limit at 5 from the left? Looks like it's at 2, right? 5 comma 2. What about 5 from the right? What's it look like to be? 2. What can you say about the full limit? It's at 2. It does exist, and it's at 2. Again, don't be tempted to say, well, look, it's gone. How can it be 2? Because, again, I don't care what's happening at 5. I care what's happening near 5. That's the idea of a limit. Okay. Let's take a look here. Find the limit as x approaches 0 if it exists. Just kind of switching gears now. Okay, so what would I do to see what the limit would be? The only, the caveman method that we know right now is to just plug in numbers, right? That's all we know how to do. So, I don't know, let's go from the right side. I like positive numbers. So I would say 1 divided by, okay, we're going to 0. Let's say 0.5. 0.5 squared. Okay. That tells me nothing right now, right? That tells me the fact, just what that value is. I need to see what it's going to. I need to see how it's moving. Okay, so instead of 0.5, let's do 0.1. Whoa. That escalated quickly. Okay, well, instead of 0.1, let's do 0.01. Does it look like it's going to anything? No. So we might be tempted to say that the limit does not exist. However, it keeps getting bigger and bigger and bigger and bigger, right? If I kept going with this, I mean, let's just go crazy, folks. Let's just insert a bunch of zeros. Insert. Okay, yeah, I guess I should have inserted that many zeros, but I keep getting bigger and bigger and bigger and bigger. Would that change if I plugged in anything with negatives? Because I'm squaring it. So no, right? This is going to evaluate the same way as if I would plug in any negatives. So as I approach 0 from both left and right sides, it keeps getting bigger and bigger and bigger and bigger. And we see the graph down below, which makes sense. Like if you think about y over x, it's going to be like an asymptote, right? At 0, or 1 over x, 1 over x. But the bigger and bigger I make, the smaller and smaller and smaller I make x as it gets closer and closer to 0, the bigger and bigger that value gets. So you know what we can say? The limit as x approaches 0 of 1 over x squared is infinity. If you can say that the limit is going to grow and grow and grow and grow, the function is going to grow and grow and grow without boundary, then you can say that the limit is going to go to infinity. And that's what's called an infinite limit. This is an intuitive definition of an infinite limit. Let f be a function defined on both sides of a, except possibly at a itself, which it's hardly ever going to be defined at a. Because we just saw right there, what's going to happen if it's going to shoot upward? It's going to be like a vertical asymptote, right? That's what we saw on the graph there. Let f be a function defined on both sides of a, except possibly at a. Then the limit as x approaches a of f of x is equal to infinity means that the function can be made arbitrarily large by taking x values sufficiently close to a. I'm going to take x, and I'm going to keep running values closer and closer to a. And when I do that, it's going to make the function really big. Really big. Okay. Again, the symbol infinity is not a number, but it's just saying that it's going to get bigger, right? It's not equal to an L where like that's going to be a finite number on the end. No. We're not capping it off. We're not defying the laws of mathematics here. We are just saying that it's going to keep getting bigger. It's going to keep going in that direction. Okay, that's what we're saying here. Yeah, we can see it here. This is another place where if you see a vertical asymptote like that and it's going to dive upward, then the limit is going to infinity. Okay. Similarly, it can dive downward. Okay, it can dive downward. You can have the limit as x approaches a of f of x also go downward. Okay, like if you just did a reflection on it, negative 1 over x squared, that just flips it downward, right? Negative 1 over x squared. That's what they're using down below. Negative 1 over x squared. It's just going to flip everything across the x-axis. So that means instead of going upward, it's just going to go downward. Same rule applies. All of those same things apply. The limit as x approaches a of f of x is equal to negative infinity means that the values of f of x can be made arbitrarily, I like the way they put this, made arbitrarily large negative. Okay. Can be made arbitrarily small negative, I guess you could say, by taking x values sufficiently close to a but not equal to a. So again, this reads that the limit as x approaches a of negative infinity, and then that's how we read that, negative infinity. It's just going to keep getting smaller and smaller and smaller. And now we can have the idea of, we know it's going to have a vertical asymptote there, but sometimes it dives up and sometimes it dives down. Okay, sometimes it goes up and sometimes it goes down. Now, here's a very important thing that we have to say. Oh, of course. This board goes out again. Somebody put in a complaint to Mr. Pilata. The vertical line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. Not all of the following statements, but at least one of the following statements. Just one of them means that you're going to have a vertical asymptote. Okay, let's read through these. The limit as x goes to a of f of x is equal to infinity. That means on both sides of the vertical asymptote, it's going to go to infinity. It's going to go up. There is also a vertical asymptote when x approaches a from the left, goes to infinity. What's that mean? That means that if I've got a function and it's going up only on the left side, there's still a vertical asymptote there. Same thing is true. I could repeat that whole statement on the right side as well. You know, this is a little bit more powerful statement, though, because that is demonstrating the fact that, well, if you've got a line A, then it's going to go up and up, right? The second statement says, well, only on the left. The third statement says, well, only on the right, right? The second statement would erase the left side of this line. The third statement would just erase away the right side of that line. And then the bottom row just basically says this. Okay, it's just going to continually further and further down there. The second statement would erase away the left side, or the right side. The third statement would erase away the left side. And it looks like we're going to, okay, we only have like a couple slides left, so the rest of tomorrow will be a work day on section 2.2. So we're going to have to push things back a little bit. That's okay. That's okay. Bummer, right? Bummer on work day. Okay. Bell rings at 9:17, right? Mm-hmm. Yeah. All right. Okay. Spend an extra day on it. Oh.